we'll start by writing out some of these probability rules. Last time we talked about how to actually compute probability, but we did more simple examples. This time we're going to look at what happens if a question says like probability of this or that, or probability of this and that, or questions like probability that something doesn't happen or not something. So let's write out some of these rules that were in the video, or that we got from before. We know that we know how to compute a probability of an event, but if we want to figure out the probability of the opposite, or not an event happening, then we simply do 1 minus the probability of the event happening. So this comes from the basic idea that an event and its exact opposite would add up to 1, because they would cover the whole sample space, right? So if you're rolling a single die, and I'll talk about all of these in terms of like a single die roll, the probability that you get a 5 on a die roll and the probability that you don't get a 5 covers the whole sample space, right? The whole sample space is rolling a 1, 2, 3, 4, 5, or 6. If I say probability of rolling a 5, and then I do probability of rolling a not 5, that covers the whole sample space, which means those two probabilities should add up to 1. So we can find the probability of not getting a 5 by just doing 1 minus the probability of getting a 5. And you'll do examples like that in today's I guess there is no there is one problem that uses the not idea. So you do 1 minus the probability of E when you want to do the negation. Next formula or rule we should have is the probability of A or B. So if A and B are events in the sample space, then to do the probability of A or B, we can split this up into probability of A plus probability of B, but we have to be wary of the overlap, which is why we subtract probability of A and B. So if A and B can happen at the same time, then we have to do this subtraction. And this is easiest to see in the form of a Venn diagram. If I have two events, and this is my event A, and this is my event B, and this is my whole sample space as the box, I want to find the probability of A or B happening, which means I want the number of elements in this joint sample, in this joint A and B joined together space, which means I want to add these two areas together. But if I add them separately like this, probability of A and B, that would be adding everything in A plus everything in B. Right, and what happens when we do that addition, just blindly adding the two spaces together, is we count this middle intersection space twice, right? That gets added in twice. So the reason why we have this minus out here is because we want to subtract one of these, so either the orange or the blue highlighted area, so that we don't count it twice. That's not going to work like that. So that we don't count it twice, we only count it once. So we'll have all of this orange space added and all of this blue space added, and then we would have also added this space once, so that we get a total that doesn't overcount anything. When you just do probability of A plus probability of B, you're blindly adding this middle space twice. So we subtract it once so that we get each space in the Venn diagram added exactly once. And then finally, if we want to do probability of event A and event B, we can simply do the probability of A times the probability of B. And that you can either do it like that, you can multiply the probability of A and B together, or you can figure out what this middle space is, because the middle space here is A and B. That's the intersection of A and B. So you can figure out how many things are in that middle intersection area. If it's like drawing cards from a deck or rolling a die, you can figure out your sample space and then your event space and do your division that way. Or you can do probability of A multiplied by the probability of B. Any questions on those rules? Okay, let me cut this off. We're going to do a problem that doesn't necessarily use one of those three rules, but it is an interesting problem to think about. So, in the question, we'll do an example here. In the question, there are two boxes. As follows. And we'll draw the two boxes. There's one box. It's kind of big. There's a second box. Oh boy. The second box, we'll call them box 1, box 2. So we can refer to them. And in these boxes, there are, does it say balls in the question? Yeah, there are colored balls in the boxes that we're going to draw out of. So we'll say that there are 5 red and 7 green balls in the first box, and the second box has 8 red and 2 green. All right, so they have different compositions of balls in the box. And there's a process. Process says, what's going to happen is one ball will be taken from box 1 without looking. So without looking. And placed into box 2. Then one ball will randomly be drawn from box 2. So one ball gets transferred from box 1 to box 2 without looking at it, and then one ball is drawn from box 2. The question we're going to ask is about this randomly selected second ball. So the question here is question is what is the probability that the ball drawn from box 2 is red. And sorry, are there any questions about the process of what's happening here? With the ball being moved from one box to the other? Anything unclear about that? Okay, then let's talk about how we would go about figuring this out. So one ball is getting taken from box 1, and that's there are two things that can happen here, right? Either a red ball gets moved from box 1 to box 2, and then the composition of box 2 changes, right? Because a red ball is now moved into box 2, and so these numbers change. And then when we draw from box 2, we have a certain number of reds and a certain number of greens, and we know how to do the probability of getting a red in that situation. Or a green ball is moved without looking, and the composition is different now, right? So we have to follow the process one ball at a time in order to split the question in the end here, because all we care about is the ball that was drawn from box 2, but the composition of box 2 is not clear until we know what happened from box 1, which one of these was moved into box 2. So what we do is we split the task into two different possible things that could happen, right? As an answer, as a structure for the answer, there are two cases. And that two cases are important. Case 1 is a red ball gets moved, and then a red ball is drawn. I guess we don't even need to say that second part. Either a red ball is moved, or case 2, a green ball is moved. In either case, we're going to do the probability, and then we're going to add these together. Since there are two cases, these are joined together with an or. Either that happens or the other one happens, right? Either a red ball gets moved from the first box to the second box, or a green ball gets moved. And since these are joined with an or, we're going to do we're going to add the two probabilities together, and we don't have to worry about this last part. Can anyone tell me why we don't have to worry about this last part? Because what if there's an overlap in the two cases? Then we'd have to subtract that overlap, right? Why am I saying we don't have to worry about the overlap? Yeah, there is no overlap between case 1 and case 2, meaning a red ball gets moved and a green ball gets moved is impossible. Right? Either one or the other one happens exclusively. So if there is no overlap, then you can just add the two probabilities together. So in case 1, we'll assume that a red ball gets, or we have to find the probability that a red ball gets moved, and then a red ball is drawn from the second one. And then in the other case, we have to find the probability that the green ball gets moved, and then a red ball is drawn from the second one. So as far as the probabilities go, we'll write it as probability that a red gets drawn from box 1, then red from box 2, plus, so that's the first case, red from box 1 gets moved to box 2, and then a red is drawn from box 2, or green gets moved from box 1, then a red gets drawn from box 2. So we're going to do those probabilities and we're going to add them together. So I guess instead of then here in the middle, I kind of want to write and, so that it's clear what kind of operation we're supposed to do. So a red gets moved from box 1 and a red gets drawn from box 2. And in the other case, we have a green gets moved from box 1 and a red gets drawn from box 2. Because remember, we're trying to find the probability that a red is drawn from box 2. So the second part of each case should be that a red is drawn from box 2. So in each of these, we'll be multiplying. So I'm going to say this turns into probability that we get a red from box 1 times the probability that we get a red from box 2 in that case, plus probability that we get a green from box 1 times the probability that we get a red from box 2 in that case. So there's two cases happening. We do the cases separately. So what's the probability that we get a red from box 1? Now we can start looking at the numbers and figuring out what fractions we have. So what's the probability that we get a red from box 1 and move it over?
Five out of 7.
Are you sure?
From box 1, right?
Yeah. Yeah, good. 5 out of 12. Because there's 12 balls, 5 of them being red. Now, when we do the second part of this from box 2, we're going to assume that a red was moved from box 1 to box 2. So what is the probability that we get a red from box 2 in this scenario? If a red is moved from box 1 to box 2, what is the probability that we get a red from box 2? Good. 9 out of 11. Because once we move a red into box 2, there are 9 reds and there are 11 total balls, so we get 9 out of 11. Okay, so then let's do the second part and see. What's the probability that we get a green from box 1? Now we're resetting because it's a totally different case, right? So the ball is no longer moved. Everything is back to its original state. What's the probability that a green gets moved from box 1 to box 2? 7 out of 12, perfect. And then in that situation where a green gets moved, what's the probability that we get a red from box 2? Good. 8 out of 11, because there are 8 reds, because the reds didn't change, but a green gets added here, so that becomes 3 greens, which means there are 11 balls, 8 of them being red. And now we just calculate. So that's what do we get here? We get 5 times 9 is 45 out of 11 times 12, which is 132, plus 7 times 8 is 56 out of 11 times 12, which is also 132. And then we have common denominators, so we can add these together. We have common denominator, we can add these together. That's 101 out of 132. So that is the probability that we get a red out of box 2 after moving one ball from box 1 to box 2. And that's a pretty high probability, right? That's pretty close to 100% because 101 out of 132 different outcomes is what we're getting there. And the reason why it's so high, or it shouldn't be surprising that it's so high, since we have so many reds in box 2 to begin with. So either a red gets moved and that increases the number of reds, or a green gets moved and it slightly increases the number of greens, but there's still a lot more reds in the second box. So the fact that there's a lot of reds in the second box makes it okay, or makes it understandable that this percentage, or this probability, is pretty high. Okay, any questions on this box problem? Or 2 boxes problem. There's a problem like this in your in-class worksheet today, so you'll be working on one of these in your groups, and then you're doing some dice problems and some playing card problems as well.